So now let's take a look at some examples. So we're going to give an example of how you detect hazards. So here we have a bunch of instructions, and we see the first instruction has its destination of R2. That is, it's going to write its results into R2. Let's take a look and see if there's a hazard between the subtract and the AND. So the subtract has its destination of R2, and the AND has a source of R2. And so what our detection logic for detecting hazard will do is say that in the memory stage, the destination register is the same as the execution register source stage. So that is, when the subtract instruction is in the mem stage and the AND instruction is in the execute stage, the hazard detection logic is going to see that there's a hazard there. How about between the subtraction and the OR? Well, the OR also uses R2 as one of its source registers. So its logic is going to see that when the subtraction instruction is in the write back stage, its destination is going to be the same as the OR instruction's source register when it's in the execute stage. So these are 2 cycles apart, so now it's going to be a hazard between the execute and the write back stage. We've also got this add instruction here, which uses the R2 as its source as well. Is there a hazard between the subtract instruction and the add instruction? No, there isn't, and that's because the subtract and add instruction are 3 cycles apart. So the double pumped register file takes care of this hazard. So we can see that here. So we saw already that for these 2 instructions we have a hazard, but for the add instruction, what we see in cycle 5 is that the subtract instruction writes into the register file in the first half of the cycle, and the add instruction reads from the register file in the second half of the clock cycle, so our double pumped register file takes care of this. So for the add instruction, there's no hazard. Now, we need to stall the pipeline to deal with these hazards. We need to wait until the data is available for things where the data isn't available on time. And how do we do that? Well, we mentioned this a little bit earlier. The key insight is if an instruction doesn't write its result, it's as if it never executed. So a stalled instruction needs to avoid writing to the register file, writing to memory, or updating the program counter. How do we do that? Well, we need to turn off those writes. So the result of this is that the instructions go through the pipeline, but they don't make any changes. And because the PC is not being updated, we keep loading the stalled instruction. So when we put in this stalling, we've converted the instruction to a bubble by disabling its writes. And we'll see that now in the next example. So in order to do this, we need to be able to detect these hazards. And if we're going to start stalling in the instruction decode stage, we need to detect them early. So how do we detect if we need to stall in the instruction decode stage? Well, to do that, we need to compare the register sources of the instruction in the instruction decode stage and see if any of the subsequent instructions are going to write to it. So we need to take the source registers of the instruction decode instruction, and we need to compare them to the destination registers of the execute stage and the destination register of the memory stage. When we compare these together, we'll be able to detect if either of the instructions in the next 2 stages is going to write to this instruction's source registers, and that lets us know we need to stall. So by doing this, we can detect if we need to stall in the instruction decode stage and insert bubbles. So let's take a look at an example here. So here we go ahead and we start executing our instructions. And now in clock cycle 3 here, our logic detects that the execution stage's destination register equals the decode stage's source register. That is, we're going to have a hazard here. And now we can go ahead and insert a bubble. That is, we're going to convert this AND instruction into an instruction that doesn't write anything to delay it. Because we've got a bubble, our PC is not updated, so in the next instruction we're going to have the same one we had before. So now we can go ahead and execute our next cycle, and for this next cycle we're going to detect that the execute stage destination instruction is the same as the memory stage's source instruction. So we need another bubble. We insert the next bubble, and again, because we inserted a bubble, our PC isn't updated, we go on to the same instruction again. Now we have our next cycle, we've got these bubbles going through the pipeline, but now we can continue because we don't have any hazards. So we go ahead and we continue to execute our instructions, and now our program works correctly. We've inserted bubbles to delay this second AND instruction sufficiently that we don't have any hazards. So when we've done this, we've inserted these bubbles in the pipeline, what percentage is the pipeline full in this example? How much useful work is there in the pipeline? Well, the answer is only 60%. So in the picture you see here, we have 3 instructions finishing in 5 cycles. In clock cycles 6 and 7, we just have bubbles, so we don't do any useful work. So again, the efficiency of the pipeline is dependent on keeping it full of useful instructions. Another approach to solving this problem is to have the compiler insert stalls, or no-ops. No-ops are instructions that don't do anything, no operation. And we can do a no-op by doing add R0, R0, R0. This says add 0 plus 0 and store it into R0. Since we can't write to R0, this has no effect. So if the compiler inserts these 2 no-ops into the code, then we don't have to do any hazard detection because we push the instructions far enough apart. But this means the compiler has to understand the pipeline in order to be able to insert no-ops in the right point. It's also worth mentioning here we're still wasting 2/5 of our cycles. Now we're not doing bubbles, we're doing no-ops. But again, these don't do any useful work, so this still slows down our program. So question, what happens to a program with compiler inserted no-ops when it runs on a newer processor with an 8-stage pipeline? Well, it's not going to work correctly because it doesn't have enough no-ops. An 8-stage pipeline is going to require more no-ops to make sure that the data hazards are avoided. If the program was compiled for a 5-stage pipeline, then some of the results won't be ready and the instructions will calculate the wrong results. This is why it's better to have the hardware insert bubbles than it is to have the compiler try and write exactly the right code. So what is the performance impact of these no-ops? So what is the IPC, instructions per cycle, of a 5-stage pipeline where 2 no-ops have to be inserted after every instruction? Well, it's going to be 0.33. So if we have 2 no-ops after every instruction, the pipeline will only complete 1 instruction every 3 cycles. This means we'll get 1 useful instruction every 3 cycles, or an IPC of 0.33. So this is much worse performance than the IPC of 1.0, 1 instruction per cycle, that an ideal pipeline can achieve.